Okay, so today we're going to start off with our definition of this concept called momentum. Try to keep it really short and sweet here. So all momentum really is like if you have an object moving at a certain speed, that object has mass, you multiply the mass and the velocity, you have momentum. So definition, so I have a mass here. Let's say he's moving along at speed v. You multiply those together, that's momentum. P for momentum. And, M for mass, etc. And V for velocity. As you can probably guess, momentum is a vector. It has a size, it has a value, and it has a direction. So it can point east, west, north, south, right, left, up, down, so it is a vector. Vectors have size, magnitude, and it points somewhere, direction. So it has a particular size and direction. Okay. So if it's just moving along and there's no outside force to disturb it, it's going to continue to move at that one momentum. Just going back to Newton's first law, if an object is in constant velocity, it's going to stay in constant velocity unless an outside force acts on it. So let's say for example, if this mass was a hockey puck and it was hit, by hockey stick, a hockey player comes in there and hits it with a hockey stick. So it's going to change from its initial velocity that it was going to, like here would be a collision between the hockey puck and the hockey stick, and then it's probably going to veer off at, it's going to veer off at some greater velocity, let's say. So its speed increases. Try and draw that better. And say collision here, and then the final case would be, something like that, larger velocity. So there's going to be an initial phase. So it has an initial velocity. The hockey stick comes in, hits the puck, and we're going to see that this action that takes place is like an equal sign, very similar to what we were dealing with when we're dealing with conservation of energy. So we're going from an initial to a final. We'll be getting to that shortly. So this hockey puck comes in, hits the hockey stick comes in and hits the hockey puck, and then the final case right here, it moves at a larger speed, let's say, or it could move at a smaller speed. But the point is, the speeds are going to be different from the initial case and the final case, okay, by the introduction of an outside force. So we had let's say we have, some net force applied onto the puck by this hockey stick, and it changes the speed from VI to V final. Okay, so it's no longer just constant momentum as we saw up here, as we saw in the case above. P equals mv is just moseying along, and then the hockey stick comes in and changes the speed. So what we do know about the situation initially is that by Newton's second law, the net force applied on an object is equal to mass times acceleration. And in terms of these velocities that we have, the initial velocity and the final velocity, we can represent this equation as mass times change in velocity over change in time, because acceleration is delta V over delta T from first principles, delta V over delta T. So we just make a substitution. So what we have here in terms of the velocity, F net is equal to M delta V over delta T. And so obviously when you reduce that delta V of delta T, you get acceleration, mass times acceleration. So this equation here indicates that there's going to be some change in momentum over change in time. And why is that? Because we know that a momentum by definition is P equals mv. So when we have m delta v, we've changed the momentum. We changed the momentum by the application of a force. So F net is going to be delta P over delta T. This is what we get here in our numerator. Because P equals mv, then if we change the momentum as we did by the application of an outside force, this delta P is mass times change in velocity. Change in velocity is going from an initial to a final. So the difference, the delta V here, is going to be final minus initial speed. So then when we take this step further and we multiply both sides by delta T, which is the time interval required to change the speed, because anytime we have a change, it requires some amount of time, whether it's 0.0001 second or 100 seconds. It's some kind of time interval required to change the action of something, to change the velocity of this mass, for example. So we multiply both sides of the equation, we have F net delta T equals change in momentum, delta P. So we just, because we multiply delta T over here and then delta T right there, and this is our final equation. So the equation on the left-hand side has been regarded as what is called the impulse. And, abbreviation for that would be I. So impulse is going to be equal to delta P, which is change of momentum. So I'm just, write that out verbally. This equation here then is known as the impulse momentum theorem, very similar to, if you would recall, the work energy theorem. So I'm just going to write those guys out. So I'm just going to take out the net, because we understand that it is a net force that's going to be required to change the speed. And what we have here is F delta T is going to be equal to delta P. That is the what is called the impulse momentum theorem, very similar to the work kinetic energy theorem. Not asking you to memorize that, but it's very similar to that theorem we've seen before. So there's an application of a force that will produce an impulse in a certain amount of time, and that impulse is going to be equal to a change of momentum there. So I'll let you get that here in a minute. Are there any questions thus far? Anything you need to see? And again, just to mess around with that. Okay, impulse is a vector, just like momentum. Force times delta T, delta P. Vector times a scalar gives you a new vector. So Solid vector. It has magnitude or size and direction. So we went from the easy case of mass times velocity, it's just a momentum moving along. Pretty much another way we can express Newton's first law: an object in constant velocity is going to stay that way, stay that way, stay that way. The momentum will never change unless we have an outside force to perturb or disturb the system, changing the velocity from an initial velocity to a final velocity. And the application of that force in a certain amount of time is what we call the impulse. So another example of that is if I have the ball, you play racquetball or something like that, or tennis or something, and the ball's coming at you at a certain speed, initial speed, and then let's say, extend it out, I guess, and then it hits a wall and it rebounds back at some final speed. Well, even if the speed is the same size, it has changed direction. So remember, a vector gets changed if the size and or the direction changes. So it hits this wall here. The wall applies a force in a certain amount of time, could be a very small, 1 microsecond or 1/10 of a second or something. So the wall applies a force, overall force in a certain amount of time, the time interval. So the wall is applying the impulse on the ball to change the momentum of the ball. So this is just another example. We can go from, the hockey puck can change the speed, the wall can change the speed. Any outside force can change the speed. A baseball bat changes the velocity of a baseball coming in from the pitcher. The guy hits it out to the outfield or for a home run. The velocity has changed size and direction. It's been hit the other way and it has a faster speed. So this is another case of an impulse being applied by this force here to change the momentum of the ball. So now we can extend this out. We know that delta P is mass times change in velocity. Delta V is also equal to final velocity minus initial velocity. So those are all equivalent statements. This depends on what we have. And we can find the impulse here by using any of these equations on the right. So again, impulse, which is F delta T, you can rewrite it this way. It doesn't matter. F delta T equals delta P, or I equals delta P. It's the same thing. Yeah. So now let's get to the business of this graph. That if you're looking at your ebook, textbook, the first graph on page 214, page 78 of the ebook. All right. So really all that's going on in that graph is when we look at force times time, when we multiply these two guys together, we get impulse, right? So that graph is really just a graph of, as we can see, F net or force is a force time graph. And generally speaking, if we have, we're gonna take our forces to just be an average value. So the force is not going to change. So if I hit the ball with a certain force, and let's say that I hit it at t equals 0, and I'm going to go and hit it up to t final, whatever that is. So this is going to be T initial, T equals 0. So the baseball is coming in, I hit it with a baseball bat. The force of that bat is just going to be a constant force, and that constant force is going to go from time equals 0, which is the first instant that I hit the ball, up to some final time. Since that force doesn't change, I'm just going to be graphing it something like this. So all the graph is a graph of impulse, force versus time. So for a graph like this, I can calculate the impulse that's being applied on the ball just by taking the area of this shaded region. So going back to this equation, multiplication is nothing more than just taking the area of a force time graph, which is very different from, doing the slope that we were doing before. But anytime you multiply, we're taking an area. So for example, if this was, say, force is measured in newtons, let's say that this was 20 newtons, and it took me, I don't know, 5 seconds to hit this object, but not a baseball, but some other object took me 5 seconds. So let's say that T final is 5. And T initial, of course, was 0. So if I multiply this, this height will be 20. And the base here will be, well, 5. So 20 times 5 is 100. Right? So the impulse of the ball is just going to be force times time, which is 20 times 5. And the units of impulse are Newton seconds, because force is newtons and time is seconds. And which reduces to the units of momentum. Sorry, I didn't say that before, but the units of momentum are kilogram meters per second. So let me just write that again here. So impulse, force times time. Let's say that my force was 20 newtons and the time was 5 seconds. You can clearly see that here. It's newtons times seconds. Well, 1 Newton, all right, is 1 kilogram meters per second squared. If I substitute that here, I have 100 kilogram meters per second squared times seconds. This right here was a Newton. And so one of these seconds goes away here. And so I can also say that this is 100 kilogram meters per second, which are the units of momentum. Momentum is mass times velocity. So it just goes back to say that impulse is just a change in the same units. Impulse is a change of momentum. I can express it as Newton seconds or kilogram meters per second. It's the same thing. We can see that by substitution. And so we won't be dealing with the graph that we see on page 214. Technically, that is what's happening in nature, that the force is actually going to change in a small window of time. But since that window of time is generally very small, we're going to approximate the force to be an average constant value. But in reality, it's going to be something like, something like that. And in order to really treat that properly, we'd have to use calculus to get the actual impulse. But we're keeping things simple on the first level by doing the stuff in a black box. Just keeping it simple right there. So that's a bit on that. So let's stop here a second and do a couple of examples. Righto. Third question. So 7th kilogram object. I'll just show you. You want to use your deductive reasoning here, but let's check this out. So 7 kilogram object moving at 2 meters per second. We can call this an initial speed only in the context that this is going to be an impulse problem. And we know that a force times time is going to change this velocity from 2 to something else. And that's what we're intending to find in this question. Find the resulting speed and direction of the object. So 7 kilogram object moving at 2 meters per second receives 2 impulses, one after the other, along the direction of its motion. So it just gets pushed twice and it's still going in the same direction. Both of these impulses are illustrated in figure 2, both of the graphs. Find the resulting speed and direction of motion of the object after each impulse. Now, one thing to keep in mind, even though impulse, right? So we have force times time here, and there's 2, 0. So in the first second, it gets pushed up to an average velocity or average force of 5 newtons, and then it maintains that for 1 second. So force in newtons. So this impulse up here, even though you take the area of this rectangle, it's technically a rectangle 5 and 2, this will be a positive impulse, and all of the impulses below the x-axis will be a negative impulse because it's be in the negative domain. So 1 second. And so in this case, if we were just trying to find the straight up impulse, force times time would be 5 times 2. Does everybody see that? Any issues on that at all? So anytime you have a multiplication, it's just going to be an area. Rectangle, square, right triangle, whatever. So that would be 10 Newton seconds, because force newtons times seconds, 10 Newton seconds, the impulse. And we're going to need to do something like that. Why is that? Because we have impulse is equal to a change of momentum. That's our definition that we started off with. Right, and so we have our impulse. This can be written as mass times delta V. Well, I'll even just put this part there as well. And we have a question. Isn't the time in 1? Oops, my bad. 1 second. I was looking at 2 and multiply by 2. It's 1 second interval. Yes, thanks for that. Good catch. So this is going to be 5 Newton seconds. So it's going to be 5. So this is going to be a span of 1. So times 1. 5 Newton seconds. Okay. All right. So then our impulse, which is change of momentum, which is final momentum minus initial momentum. And it's also equal to mass, final velocity, minus initial velocity, and so forth, and all of that. So if we're trying to get the initial speed, oops, F delta T, we want to use one of these expressions that has the final speed actually in the result. And the best expression is this last one here. So we have mv final, mv initial. So we can just solve for v final at this point because that's what we're looking for. So F delta T plus mvi equals mv final. And so then v final will just be F delta T plus mvi divided by the mass. And so we just put all of our numbers in here and solve it out for the final speed. So we have essentially F delta T over mass, and this is going to be plus mvi over m, or just vi because the mass is going to cancel out for that guy. And so we have our impulse up top, force times time, which is 5 Newton seconds, divided by the mass, which is 7, plus the initial velocity, which is 2. And that will be our answer. That's how we get our final speed. But it all comes from, manipulating this impulse momentum expression. So our job is, and our job is to get an expression such that we have the final velocity as part of that expression so that we can solve for it. Otherwise, it'd be a little difficult, It's not that much more difficult, but a little bit harder than just using the expression mv final minus v initial. So these are all equal to each other. Yes.
Oh, sorry. For the impulse graph, is it supposed to be 5 or -5?
Well, this one's 5 because it's above, it's in the positive domain. But in the second graph, it's going to be negative.
Okay.
Yeah. So as I was mentioned before, all of the graphs above the x-axis will be positive quantities, and below the x will be negative. And another question. Yes, I can scroll down. All right, so then we'll just solve that out. 5 divided by 7. .714 plus 2. And 2.7, as if it wasn't. And so it should make some sense. Everything's in a positive domain. It's been pushed to the right, and outside forces cause it to go from its initial speed to a final speed, still going to the right. So this answer should be positive, right? All right. Now for the second. So now the impulse is below, so that's going to be a negative impulse. So it's along the direction of motion, so it's a horizontal. It's not still going to be going to the right per se. It's going to, the impulse is negative in this case, so the final velocity should also be that. But let's confirm. We know that the impulse at least is going to be negative. But as good experimenters, good scientists, we go and test it. Has anybody ever heard of the Thunderbolts project? YouTube channel? It's a good channel. I just put it out there. It's an amazing channel. Physics related and all that good stuff. But we'll get to that in time. So that was my spring break. I was doing a lot of different ways of, not all my spring break, but different ways of thinking about the universe, if you will. So so here's our 1 second interval. -5 times 1, okay. All right, so right. So that's going to be -5 Newton seconds. And we're going to get the final speed the same way. So we can just use the same formula, really, right? So F delta T over m plus the initial velocity, which is 2. It was going to the right, 2 meters per second. Didn't really given a direction, but since the 2 is positive, assumption is to the right or positive direction. All right, so this is going to be -5 divided by 7 plus 2. Yes, that does make sense in the context, and the numbers bear themselves out. That yes, even though it's 2 impulses and one is negative, you know, it's still going to be positive here. This is 1.286 meters per second. So still to the right, still positive direction, even though the impulse was negative. Could anybody think of any possible force that could be acting in a so-called negative direction and the object will still be going to the right? What kind of force does that? If we recall.
Gravity?
We're still on the x-axis. So not gravity. Another resistive force. So if you're going to the right and you start slowing down, what could be the force causing you to slow down?
Air resistance.
Air resistance or friction. Air resistance is a form of friction. Yes, indeed. Friction. Yes, Ramiro. Yes, it is friction that's going to. So this impulse here, this force that's providing this impulse, which is going to the left or opposite you, would be friction, because friction is obviously, we can see it here. The speed is getting smaller. It's going from 2.714 to 1.286. It's got to be friction. It's got to be some air resistance. Let's say that you're walking along, or car is in a hurricane, gale force wind coming back the other way. There's some kind of air resistance that's going to slow you down. So yeah, so friction would be the nice candidate here. So that's how you do these guys. Again, it stems from the impulse momentum theorem here. F delta t, which is I equals change in P, which is also equal to mass velocity, mass times initial minus final velocity. And this will be the best choice because we're trying to find what the resultant or final velocity is. So the other forms, although equal, won't be directly helpful. And this is the best choice. So that it will do that. I think for your first homework problem set here is just to do the last 2 questions. I'll just, let's have those due by Friday when we meet up again. And so we'll do some sort of a fun Labster activity or something. And I haven't thought about it yet, but something is always going to be fun on Fridays. Tuesdays is to set things up, intro, and then Fridays we'll do something related to this, but fun. Okay, so that is that.